Bob Sedgwick, a few years ago, came up with a different balance function on red-black trees that he says is good because it reduces the number of cases in the proof. And like, who cares? Okay, those are called left-leaning red-black trees. So if you see left-leaning red-black trees, you know this is good because it reduces the number of cases in the proof, and we don't care. Yes?
Just a short question about the match goal you used. So in the goals where having the exact form match something with, and then you explicitly list two cases with the constructor, could you merge those two cases, saying, well, as long as I match something, I don't care about the patterns, I don't care about the cases, I just want to destruct what is being matched on?
So the question is, in LTAC programming, is there a form of matching the goal so that sort of any kind of match on any type could be matched, and we destruct the formula being matched on? And the answer is yes. But I wanted to be careful to understand what kinds of case analysis I'm doing and restrict my proof automation just to that case analysis so that I didn't do things in the proof that I didn't understand, right? There are 117 cases in this case analysis, but there are really only 4 kinds of case distinctions, and I'd like to understand that. So that was by choice. Okay, so that was just a warm-up. We've got to prove the search tree property, right? You've seen the proof about binary search trees, so now we've got to prove that red-black trees are binary search trees. What is the search tree property? That the value of the key at any node is greater than the values of all the keys in the left subtree and less than the values of all the keys in the right subtree. And we need to prove that the balance function preserves that property when it does rotations. Okay, so that's this theorem, balance search tree. This property is just the same as you saw in the last lecture about search trees. And this theorem, right, if S1 is a search tree with range low to K, and S2 is a search tree with range K plus 1 to high, then balance C S1K KV S2 is a search tree with range low to high. So that's the theorem. We will not need induction because balance is not a recursive function. It's just a couple of levels deep. It's a little trivial pattern match. So that's what we need to prove. Okay. And let's start with some proof automation. If our proof goal matches this, we're proving the search tree property on a pattern match of red or black, or a pattern match of E or T, then destruct the argument of the match. So that's this proof automation. Okay, repeat, match goal with those 2 clauses. There are 58 cases. All right, and some of the cases are quite easy. If I just apply constructor here, well, it'll apply the search tree rule for T, and then now I have to prove these 2 subgoals, and that's exactly what I have above the line. I think this case is so easy because in this case, balance didn't do any rotations, right? And I already had in the premises of the theorem the search tree properties of the 2 cases that I wanted. So constructor semicolon auto proves this goal. And the second case, ditto. And the third case. And here, I think still balance isn't doing any rotations, but it's examining the subtrees. It took them apart to a greater depth. So when I do this first constructor auto, I have subgoals that aren't identical to the one above the line. But if I do another constructor auto and another, Okay, so now I have to prove this. K plus 1 is less than or equal to K0. And how could I prove that? Do I believe it? Here's K plus 1. That's the lower bound of this search tree that contains the key K0. So that's good. If we invert H0, that should prove what we need. But that's already too much thinking. Let's just invert everything in sight. So invert H, that was useless, but it doesn't hurt us any. Now we invert H0, that was actually useful, but we don't know why. Let's invert H8 and H9. We still have more things that we can invert, but actually by now we've proved the goal. Okay, so let's do constructor auto and see what it is we have to prove. We have to prove this. Let's invert a lot of things and then see if one of them proves it. Okay, so every time we have search tree prime above the line, let's invert it. Okay, so that's the pattern. If we have something above the line that looks like search tree prime on E, invert it. If we have something above the line that looks like search tree prime on capital T, we should invert it. But if it's search tree prime on a variable, then inversion won't tell us anything useful, so don't invert it. Okay, so let's do that proof again. This is what we had before in the pattern match, and this is what we've added. So look, here's the turnstile. This turnstile represents the line. And this says above the line there's some hypothesis, whatever its name is doesn't matter, but here we will call it H. Whatever its name is, bind that to H if it matches this pattern. And this, here we say below the line. In this case we don't care what's below the line, so put an underscore there. And if our proof goal looks like that, then invert H. And if our proof goal looks like that, invert H. So let's do that. There's still 58 cases to consider. These inversions didn't prove any cases. They just did some work above the line in those cases. But now, just constructor auto, constructor auto. We just keep doing constructor auto. So let's add constructor auto to our automation. First, we're going to do the repeat. That will leave us 58 cases. Then we have the all-important semicolon, which says, in every sub-goal, do this. All right, so QED. Question?
What's the reason that H in the assumption doesn't need a question mark in front of it? Is that just the syntax of...
The reason is because. All right, so the question was, why does the H in the pattern match for the hypothesis not need a semicolon, not need a question mark? And the answer is because that's the definition of the LTAC language. It doesn't need it. Okay, so if you want to do the, yes, question.
Is there a reason you're not adding the constructors to the database to just auto it?
Oh yes, well, there's a way that you can add all the constructors of an inductive type to the hint database. You say hint constructors, and then auto would do them automatically. Here I'm being very parsimonious with this proof automation. I'm just doing only enough magic to prove this theorem. And the alternative is to predict in advance that we're going to want all magic all the time. And so you add all these constructors to the hint database, and you make a general purpose tactic that does these kinds of destructs, and then you use it everywhere. And this is a fine way to proceed as well. But for this sort of explanation of what we're doing, I want to take it quite carefully. All right, now, if you were going to do the red-black tree homework, which you don't have to do because early next week, there will be more lectures with more homework. And I think it's really useful for you to do the binary search tree homework, but at some point you have to choose which things you're more interested in proving. But you could prove some of this with proof automation. It's kind of fun. Insert produces a search tree, and really you're just going to paste in your proof from the ordinary search trees file that insert produces a search tree. But at one place where you had a T in the other program, you have a balance here, and you'll just apply this lemma. So this is easy, not a lot of case analysis, no need for proof automation. Let's see. A lot of these other functions you won't need much proof automation. But if you're going to just do one theorem in the homework for red-black trees, try this one. It's called balance relate. And it says, if T is a search tree and it abstracts to some total map M, then the rebalance of that search tree abstracts to the same total map M. And you can see that that might be useful in a proof of insert relate. Okay, so let's prove it. Intros, invert H, unfold balance. Okay, so this is what you have to prove. That abstracts to M. If that abstracts to M, so yeah, let's do it by hand. And we could prove that one. In proof goal 2, let's destruct L. And in 2, let's destruct R. And in 3, let's destruct C. All right, let's not do this by hand. It'll have 117 cases. You could do it by hand. I think in one afternoon you could do this by hand. It's not that much typing, especially when you can copy-paste. But really, this is not the way to prove things. The way to prove things is to use tactic programming. So the comments in this homework exercise explain what clauses you'll want in your tactic pattern match. And you can implement this yourself and see it go. All right, now, having seen all that, without understanding the balance function, who believes it's correct? Okay, because we wrote a program that proved it's correct. While doing that proof, we didn't see the proof because the program built the proof. So we don't actually understand the details of the balance function, but we know that there's a program that proves it correct. Isn't that great? Okay, so what?
Sat solving.
That's like sat solving. Okay, right. So I think this is one of the important features of Coq, or of really any proof assistant, is that it comes with a tactical programming language. And some proofs we really do want to automate because they have lots of case analysis. Now, there's other ways of automating proofs besides tactic programming. You can do proof by reflection, where your programming is actually inside Galena, inside Coq's own functional programming language. All right, so that is the end of this lecture. I'm going to stop early to leave you more time to do the homework after lunch. And sometime on your own, you could explore other interesting parts of verified functional algorithms. For example, binary tries. If you want efficient lookup tables from Coq's Z-type, you want to have a tree that indexes on the bits of the integer. And this is a beautiful data structure, and not only is it reasonably easy to prove correct, but that proof of correctness is an essential part of the CompCert verified optimizing C compiler, which uses this data structure all over the place. And then binomial queues. This is a beautiful data structure. Not so useful, actually, as the other one, but in some cases it can be useful. It's priority queues with log n time for insert, log n time for delete min, and log n time for merging two queues together. And it's great fun to do the proof of this thing in Coq because it implements very well as a pure functional algorithm. So when you have the time, have some fun doing these proofs about functional programs. And that's it for today.